Photons that began their journey when the universe was only 380,000 years old are striking your eyes through your screen. These ancient messengers traveled for over 13 billion years to reach you, carrying information from the edge of everything we can ever hope to see. But here is what makes this absolutely mind-bending. Those photons didn't travel 13.8 billion light years to get here. They traveled over 45 billion light years. For centuries, we assumed the observable universe was simple to calculate. Light travels at a fixed speed. The universe is 13.8 billion years old, so obviously we can see 13.8 billion light years in every direction. The observable universe should be 27.6 billion light years across. We were completely wrong. The real answer is 93 billion light years across, more than 3 times larger than our logical assumption. This isn't some exotic theoretical prediction. This is measured, verified, undeniable reality. The Planck Space Telescope, launched in 2009, mapped the cosmic microwave background radiation with unprecedented precision. Those measurements confirmed what cosmologists like Alan Guth and Andre Linde had calculated. Space itself has been expanding faster than light for most of cosmic history. When we observe the most distant galaxies through the Hubble Space Telescope and the James Webb Space Telescope, we're seeing objects that are now over 46 billion light years away, even though their light has only been traveling for 13 billion years. Think about this for a moment. You are sitting at the center of a sphere that contains everything humans will ever be able to observe. Every star, every galaxy, every wisp of cosmic gas, it all exists within this boundary. Beyond this edge lies the unobservable universe, forever hidden from us not by technological limitations, but by the fundamental structure of space-time itself. And this sphere surrounding you is almost incomprehensibly vast, so large that if the Earth were the size of a grain of sand, this cosmic sphere would still be larger than our solar system. But tonight we're going to discover why this boundary exists, how we calculated its true size, and what this reveals about the most profound questions in cosmology. We'll explore how the expansion of space creates a cosmic horizon more absolute than any physical barrier. We'll uncover why the geometry of space-time makes distant objects appear closer than they actually are. And we'll confront the unsettling reality that 99.999% of the universe may be forever beyond our reach. Dr. Brian Greene describes this as the cosmic loneliness principle. We exist in an island of observability, surrounded by an infinite ocean of the unknowable. Dr. Neil deGrasse Tyson calls it the ultimate humbling, a reminder that even our grandest surveys of cosmic structure reveal only the tiniest fraction of what exists. Subscribe and hit that thumbs up if you're ready to understand why the universe is far stranger and more isolated than we ever imagined. And here is a question that will bend your brain. If we can see galaxies that are now 46 billion light years away, how long would it take light from Earth to reach them today? Drop your answer in the comments. I'll pin the most insightful response. What we're about to explore isn't just astronomy. It's a journey into the deepest nature of reality itself. We'll discover that the universe has built-in limits that no technology can overcome. We'll learn that cosmic expansion creates paradoxes that challenge our intuitive understanding of distance and time. And we'll realize that every observation we make is simultaneously a look into the past and a glimpse of objects that have moved unimaginably far away. The story begins with a simple question that leads to the most mind-expanding revelations in modern science. When we look up at the night sky, how far can we actually see? The answer will transform your understanding of space, time, and your place in the cosmic order. Now let's begin this journey to the edge of everything. Chapter 1. Cosmic Horizon. Every night when you look up at the stars, you're staring directly at the edge of reality itself. Not because space ends somewhere out there, But because there exists a fundamental boundary beyond which information cannot reach us, this boundary isn't physical. It's woven into the fabric of space-time itself. Tonight, we recrossing that threshold to understand why the observable universe has limits that no telescope will ever overcome. The concept seems straightforward at first. Light travels at a finite speed, 299,792,458 meters per second, or about 186,000 miles per second. The universe has existed for approximately 13.8 billion years since the Big Bang. Simple multiplication suggests we can see objects whose light has been traveling for up to 13.8 billion years, creating a sphere around us with a radius of 13.8 billion light years. This gives us an observable universe roughly 27.6 billion light years across. But this calculation makes a crucial assumption that the universe has remained static while light traveled through it. Reality is far more complex and far more fascinating. Space itself expands, and this expansion affects every photon's journey in ways that completely transform our cosmic perspective. In 1929, astronomer Edwin Hubble made the observation that would revolutionize our understanding of cosmic scale. Working with the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble measured the distances to nearby galaxies using Cepheid variable stars as cosmic lighthouses. He then examined the light from these galaxies using spectroscopy, revealing something extraordinary. Nearly every galaxy showed a redshift, meaning their light was stretched toward longer, redder wavelengths. This redshift pattern followed a precise relationship. The more distant a galaxy, the greater its redshift. Hubble realized he was witnessing the expansion of space itself. Galaxies weren't moving through space. Space was carrying them apart. This discovery meant that light traveling through an expanding universe experiences a very different journey than light traveling through static space. Consider a photon emitted from a distant galaxy 10 billion years ago. As this photon travels toward Earth, the space it moves through continuously expands. The galaxy that emitted the photon moves farther away with each passing moment. By the time the photon reaches us, that galaxy has traveled to a location much more distant than where the photon began its journey. To understand this properly, imagine an ant walking across a balloon while you inflate it. The ant maintains a constant walking speed, but the balloon's expansion carries the ant's starting point farther away as it walks. When the ant finally reaches its destination, the distance between start and finish has grown much larger than the distance the ant actually walked. This analogy reveals why cosmic distances are so counterintuitive. We can see galaxies whose light has traveled for 13 billion years, but those galaxies are now over 30 billion light years away. The light shows us where they were billions of years ago, not where they are now. We're seeing cosmic archaeology, ancient light carrying information about the universe's distant past. The expansion rate isn't random or chaotic. Cosmologists describe it using the Hubble constant, currently measured at approximately 67 kilometers per second per megaparsec. But here's where the story becomes truly mind-bending. At a distance of approximately 14 billion light years, the expansion velocity reaches the speed of light itself. Beyond this distance, space expands faster than light can travel through it. This creates what cosmologists call the Hubble sphere, a boundary beyond which objects move away from us faster than light. You might think this violates Einstein's special relativity, which states that nothing can travel faster than light. But the objects aren't moving through space faster than light. Space itself is expanding, carrying them along. Einstein's limitation applies to motion through space, not to the expansion of space itself. General relativity actually predicts this cosmic expansion, and observations have confirmed it repeatedly. This faster-than-light expansion creates profound implications for what we can observe. Light emitted today from the most distant visible galaxies will never reach Earth. These galaxies are crossing beyond our cosmic horizon as we watch them. Future astronomers will see fewer galaxies than we do, not because of technological limitations, but because cosmic expansion is carrying more objects beyond the reach of their light. The cosmic horizon represents the ultimate observational boundary. No matter how powerful our telescopes become, no matter what new technologies we develop, we cannot see beyond this limit. Information from beyond the horizon cannot reach us because space expands too quickly for light to make the journey. Dr. Lawrence Krauss describes this as cosmic censorship. The universe has built-in privacy settings that hide most of its contents from any observer. We exist in what amounts to a cosmic bubble of observability, surrounded by an infinite realm we can never explore directly. The mathematics of this boundary reveal something profound about the nature of observation itself. Every point in the universe sits at the center of its own observable sphere. An alien astronomer in a galaxy 50 billion light-years away would see their own cosmic horizon, with Earth forever beyond their observational reach. The universe provides each location with its own unique perspective, its own limited window into cosmic truth. This boundary isn't just a curious astronomical fact, it's a fundamental feature of reality. It means that cosmology, the study of the universe as a whole, must be constructed from an inherently limited dataset. We can see only a tiny fraction of what exists, and we must infer the properties of the entire universe from this small sample. As we stand on Earth looking outward, we're seeing the universe as it was, not as it is. The most distant objects visible through the Hubble Space Telescope show us galaxies as they appeared over 13 billion years ago, when the universe was young and very different. These ancient galaxies have evolved, merged, or perhaps even died during the billions of years their light has been traveling toward us. This creates a profound paradox of cosmic observation. The farther we look into space, the farther we look back in time. Our view of the universe resembles an archaeological dig more than a photograph. Each distance corresponds to a different epoch in cosmic history, creating a timeline that stretches from the present back to the universe's infancy. But this is only the beginning of our journey into cosmic scale. The true size of the observable universe, that mind-bending figure of 93 billion light-years across, emerges from an even deeper understanding of cosmic expansion and the geometry of spacetime itself. Chapter 2. Hidden Expansion. The universe has been keeping a secret from us, hidden in plain sight for over 13 billion years. While we calculated cosmic distances using the simple assumption that space remains static, the universe has been playing by entirely different rules. Tonight, we re-uncovering the mechanism that makes the observable universe nearly 3 times larger than our initial calculations suggested, and why this discovery revolutionized our understanding of cosmic evolution. When astronomers first began measuring cosmic distances in the early 20th century, they faced an unprecedented challenge. How do you measure the distance to objects so far away that conventional methods become useless? The breakthrough came through the work of Henrietta Swan-Leavitt, who in 1908 discovered a relationship between the brightness and pulsation period of Cepheid variable stars. These stellar lighthouses provided the first reliable cosmic distance indicators. Edwin Hubble used Leavitt's discovery to measure distances to nearby galaxies in the 1920s. But when he examined the light from these galaxies through spectroscopy, he found something completely unexpected. The spectral lines of hydrogen, helium, and other elements were shifted toward the red end of the spectrum. This redshift initially seemed to indicate that galaxies were moving away from us at tremendous speeds. The pattern was even more surprising. Nearby galaxies showed small redshifts, indicating modest recession velocities. More distant galaxies showed larger redshifts, suggesting they were racing away at ever-increasing speeds. The most distant galaxies observable with 1920s technology appeared to be fleeing at velocities approaching a significant fraction of the speed of light. But Georges Lemaître, a Belgian physicist and Catholic priest, proposed a radical interpretation in 1927. Rather than galaxies moving through space, Lemaître suggested that space itself was expanding. This wasn't motion in the conventional sense. It was the metric expansion of the cosmos, a stretching of the very fabric of space-time. Einstein initially resisted this idea, famously calling it the biggest blunder of his career when he realized his own general relativity equations predicted cosmic expansion. But observations continued to support Lemaître's interpretation. By 1931, Einstein had accepted the evidence and embraced the expanding universe model. This expansion creates effects that completely transform how we understand cosmic distances. When a photon begins its journey from a distant galaxy, it starts with a specific wavelength determined by the atomic transitions that created it. As this photon travels through expanding space, the expansion stretches the photon's wavelength, shifting it toward the red end of the spectrum. The amount of redshift directly correlates with how much space has expanded during the photon's journey. A galaxy showing a redshift factor of Z equals 1 has had its light wavelength doubled during the journey to Earth. This means space has expanded by a factor of 2 since the light was emitted. For Z equals 2, space has expanded threefold. For Z equals 10, space has expanded by a factor of 11. The James Webb Space Telescope has now observed galaxies with redshifts exceeding Z equals 13, meaning space has expanded by more than 14 times since those galaxies emitted their observed light. These observations are revealing the universe as it appeared less than 400 million years after the Big Bang, when the first stars and galaxies were just beginning to form. But here is the crucial insight that transforms our understanding of cosmic scale. While the light has been traveling toward us, the galaxy that emitted it has been carried to much greater distances by cosmic expansion. We see where the galaxy was when it emitted the light, but the galaxy itself has moved to a completely different location. To calculate the current distance to objects we observe, astronomers must account for all the expansion that has occurred during the light travel time. This calculation reveals distances that dwarf the simple light travel distance. A galaxy whose light has been traveling for 10 billion years is now located approximately 17 billion light-years away. A galaxy whose light has traveled for 13 billion years is now over 30 billion light-years distant. The mathematics of this expansion follow precise cosmological models. The standard lambda-CDM model incorporates 3 key components: ordinary matter, dark matter, and dark energy. Each component affects the expansion rate differently throughout cosmic history. During the universe's early epochs, matter and radiation dominated, causing the expansion to decelerate. More recently, dark energy has become dominant, causing the expansion to accelerate. This changing expansion rate creates a complex relationship between redshift, light travel time, and current distance. The Planck satellite mission, which operated from 2009 to 2013, measured the cosmic microwave background radiation with extraordinary precision. These measurements provided the most accurate determination of cosmic parameters ever achieved, allowing astronomers to calculate distances with unprecedented accuracy. The results are staggering. The most distant objects we can observe, the sources of the cosmic microwave background radiation, emitted their light when the universe was only 380,000 years old. This radiation shows a redshift of approximately Z equals 1090, meaning space has expanded by over 1,000 times since this light was emitted. While this ancient light has been traveling for 13.8 billion years, the regions that emitted it are now located over 46 billion light-years away. This creates the observable universe's true scale. In every direction, we can see to a distance where objects are currently located 46.5 billion light-years away. The observable universe forms a sphere with a radius of 46.5 billion light-years, giving it a diameter of approximately 93 billion light-years. But cosmic expansion affects more than just distances. It transforms the very nature of observation itself. When we look at distant galaxies, we're not just seeing them as they were in the past. We're seeing them compressed by cosmic perspective effects. Galaxies that were much closer to us when they emitted their observed light now appear smaller and fainter than they would if space were unexpanding. The expansion also affects the rate at which we receive information from distant sources. Light from a galaxy at high redshift arrives at Earth stretched not only in wavelength but also in time. Events that occurred rapidly in the distant galaxy appear to unfold more slowly from our perspective. We're watching cosmic history in slow motion, with the effect becoming more pronounced for more distant objects. Dr. Saul Perlmutter, who won the Nobel Prize for discovering cosmic acceleration, describes this as viewing the universe through a time machine with a zoom lens. Every observation simultaneously reveals information about cosmic history, while showing objects that have since moved to completely different locations. The implications extend far beyond astronomy. Cosmic expansion means that the universe we observe today represents only a tiny fraction of what has existed throughout cosmic history. Countless galaxies have moved beyond our cosmic horizon since the universe began. We're seeing an ever-diminishing sample of cosmic reality. Furthermore, cosmic expansion is accelerating. Dark energy, which comprises approximately 68% of the universe's total energy density, drives this acceleration. This means that in the far future, fewer and fewer galaxies will remain observable from Earth. Future astronomers, billions of years from now, will inhabit a darker, more isolated cosmos as expansion carries more objects beyond the cosmic horizon. The discovery of cosmic expansion and its effect on observable distances represents one of the most profound revelations in the history of science. It transformed our understanding of the universe from a static, eternal structure to a dynamic, evolving cosmos with built-in observational limits. Yet this is only the beginning of our exploration into cosmic scale. The true nature of the observable universe's boundary emerges from an even deeper understanding of how light propagates through curved spacetime, and how cosmic expansion creates paradoxes that challenge our fundamental concepts of distance and reachability. Chapter 3. Impossible geometry space has a shape that defies every intuition we've developed about geometry, distance, and the nature of reality itself. Tonight, we're entering a realm where straight lines curve, parallel paths converge or diverge, and the shortest distance between 2 points might not exist at all. The 93 billion light-year diameter of the observable universe emerges from space-time geometry so strange that it transforms our basic understanding of what it means for something to be far away. Albert Einstein's general theory of relativity, published in 1915, revealed that space and time aren't separate entities, but form a unified four-dimensional fabric called space-time. More revolutionary still, this fabric isn't rigid. It bends, warps, and curves in response to the presence of matter and energy. What we experience as gravity is actually the curvature of spacetime itself. But Einstein's equations predicted something even more extraordinary. On cosmic scales, spacetime itself can expand, contract, or reshape itself in ways that completely transform the meaning of distance. The universe's geometry isn't fixed. It evolves according to the matter and energy it contains. In 1922, Alexander Friedmann solved Einstein's field equations for a homogeneous isotropic universe and discovered 3 possible geometries. The universe could be flat, Euclidean, closed, spherical, or open, hyperbolic. Each geometry creates radically different rules for how distances, volumes, and cosmic evolution behave. The Planck satellite measurements revealed that our universe is remarkably close to flat geometry. So close that it may be exactly flat. This flatness isn't accidental. It's a consequence of cosmic inflation, a period of exponential expansion that occurred during the universe's first fraction of a second. Inflation stretched any initial curvature to such enormous scales that our observable region appears flat, just as the Earth's surface appears flat to someone standing in a field. Flat geometry in an expanding universe creates mind-bending effects on cosmic distances. In normal Euclidean space, the distance between 2 points remains constant unless the objects move relative to each other. But in expanding flat space, distances between stationary objects continuously increase as the space between them grows. This expansion affects different types of distances in distinct ways. Cosmologists distinguish between several distance measures, each revealing different aspects of cosmic geometry. The comoving distance represents how far apart objects would be if we could freeze cosmic expansion right now. The proper distance accounts for the current expansion state. The luminosity distance describes how far away an object appears based on its brightness. The angular diameter distance determines how large an object appears on the sky. These distance measures diverge dramatically in an expanding universe. A galaxy with a comoving distance of 30 billion light-years might have a luminosity distance of 50 billion light-years, making it appear much dimmer than expected. The same galaxy might have an angular diameter distance of only 10 billion light-years, making it appear larger on the sky than its redshift would suggest. The cosmic microwave background radiation illustrates these geometric effects perfectly. This ancient light comes from a spherical shell around us called the surface of last scattering. When this radiation was emitted 380,000 years after the Big Bang, the observable universe had a radius of only about 260,000 light-years, smaller than our current Milky Way galaxy. But cosmic expansion has stretched this shell to enormous proportions. The regions that emitted the cosmic microwave background are now located approximately 46.5 billion light-years away. We're seeing the afterglow of a cosmic sphere that was once tiny but has been inflated to become the boundary of everything we can observe. The geometry becomes even stranger when we consider the universe's topology, its large-scale shape and connectivity. While observations suggest flat geometry locally, the universe could still have exotic topological properties. It might be finite but unbounded, like a cosmic torus or Klein bottle. In such universes, light could potentially travel around the entire cosmos and return to its starting point. Some cosmologists have searched for evidence of cosmic topology by looking for repeated patterns in the cosmic microwave background. If the universe were smaller than the observable horizon, we might see the same cosmic structures appearing in multiple directions, like reflections in a hall of mirrors. So far, no such repetitions have been detected, suggesting the universe is either infinite or much larger than the observable region. The expansion of flat space creates another geometric paradox. The concept of simultaneity breaks down on cosmic scales. Events that appear simultaneous to one observer may not be simultaneous to observers in different reference frames. This means there's no universal now that applies throughout the cosmos. When we say a distant galaxy is currently 30 billion light-years away, we're implicitly choosing a specific time slicing of four-dimensional space-time. Other observers, moving relative to us, would calculate different current distances to the same galaxy. The geometry of space-time makes the concept of absolute simultaneous distance meaningless on cosmic scales. Dr. Max Tegmark of MIT describes this as the democracy of observers. Every location in the universe has an equally valid perspective on cosmic geometry. There's no privileged reference frame that provides the correct view of cosmic distances and simultaneity. The expansion also affects the paths that light takes through cosmic geometry. In static space, light travels in perfectly straight lines. But in expanding space, light follows geodesics, the curved paths that represent the shortest routes through curved spacetime. These geodesics stretch and bend as space expands, creating complex trajectories that seem impossible in ordinary geometry. Consider a photon emitted from a galaxy 13 billion years ago. As this photon travels toward Earth, the expanding universe curves its path in subtle but measurable ways. The photon experiences gravitational lensing from dark matter structures, deflection by cosmic expansion, and redshifting that continuously reduces its energy. By the time it reaches Earth, this photon has followed a trajectory unlike anything possible in static space. Gravitational lensing adds another layer of geometric complexity. Massive galaxy clusters bend light rays, creating multiple images of background galaxies or magnifying their apparent size. The Hubble Space Telescope has captured stunning examples of this cosmic lensing, showing distant galaxies stretched into arcs or multiplied into ghost images. These lensing effects sometimes allow us to observe galaxies that would otherwise be too faint to detect. Cosmic magnification can boost the apparent brightness of distant objects by factors of 10 or more, effectively extending our observational reach deeper into space and further back in time. The James Webb Space Telescope exploits this natural magnification to study some of the most distant galaxies ever observed. By targeting regions behind massive galaxy clusters, astronomers can observe galaxies with redshifts exceeding z equals 13, revealing cosmic history from less than 400 million years after the Big Bang. But perhaps the most mind-bending geometric effect involves the concept of cosmic horizons themselves. The observable universe as boundary isn't like a wall or surface. It has a sphere of spacetime events that defines the limit of causal contact. Light from beyond this horizon hasn't had enough time to reach us since the Big Bang began. Yet this horizon is dynamic. As time passes, light from slightly more distant objects crosses our cosmic horizon and becomes observable. The observable universe grows larger each day, revealing new regions of space that were previously beyond our reach. At the same time, cosmic acceleration ensures that objects currently near the horizon will eventually move beyond our future observational reach. The geometry of cosmic horizons reveals deep connections between thermodynamics, quantum mechanics, and gravity. The horizon has an associated temperature and entropy, properties that seem paradoxical for empty space, but emerge naturally from the geometric properties of spacetime itself. Stephen Hawking's work on black hole horizons revealed similar properties. Horizons have temperature, emit radiation, and store information in ways that challenge our understanding of space and time. The cosmic horizon shares these mysterious properties, suggesting deep connections between quantum physics and cosmic geometry. As we contemplate these geometric impossibilities, we begin to realize that the 93 billion light-year observable universe represents just the beginning of cosmic strangeness. The true scale emerges not just from expansion, but from the fundamental nature of spacetime itself, a fabric so malleable and strange that it transforms every concept we thought we understood about distance, time, and reality. Chapter 4. Temporal boundaries. Time itself has an edge, and we've been staring at it every night without realizing the profound implications. The observable universe's boundary isn't just about distance. It's about the fundamental limit of how far back in time we can see. Tonight, we're exploring how this temporal horizon shapes everything we know about cosmic history, and why the earliest moments of the universe remain forever beyond our direct observation. The concept of a temporal boundary seems counterintuitive at first. We imagine time as flowing smoothly from the Big Bang to the present, with each moment accessible if we could just look far enough into space. But the universe's history contains periods when light could not travel freely, creating temporal walls that block our view of cosmic infancy. The story begins approximately 380,000 years after the Big Bang, during an epoch cosmologists call recombination. Before this time, the universe was so hot and dense that electrons could not bind to atomic nuclei. Free electrons scattered photons continuously, making the cosmos completely opaque to light. The universe resembled a glowing fog, with light trapped in an endless cycle of emission and absorption. As cosmic expansion cooled the universe below about 3000 Kelvin, electrons finally combined with protons to form neutral hydrogen atoms. This recombination happened relatively quickly across the cosmos, clearing the cosmic fog and allowing light to travel freely for the first time. Cosmologists call this moment first light, the dawn of transparency in cosmic history. The cosmic microwave background radiation carries information from this pivotal transition. When we observe this ancient light through satellites like WMAP and Planck, we're seeing the universe as it appeared during recombination. This radiation shows us the temperature variations and density fluctuations that would eventually grow into stars, galaxies and galaxy clusters through gravitational collapse. But here's the crucial limitation. We cannot see beyond the surface of last scattering. Everything that happened before recombination remains hidden behind this opaque wall. The universe's first 380,000 years, including the epoch of cosmic inflation, primordial nucleosynthesis, and the formation of the first atomic nuclei, lies beyond direct observation. This temporal horizon profoundly limits our understanding of cosmic origins. We must infer the universe's earliest history from indirect evidence. The cosmic microwave background's temperature and polarization patterns, the abundance of light elements like deuterium and helium, and the distribution of large-scale structure in the present universe. The James Webb Space Telescope has pushed our observational reach to within 400 million years of the Big Bang, revealing the first galaxies and stars. But even these ancient objects formed long after recombination. The universe's true infancy, those crucial first moments when space, time, and matter assumed their basic properties, remains hidden behind the temporal wall. Theoretical physics suggests even earlier temporal boundaries may exist. During cosmic inflation, which likely occurred during the first 10 to 32 seconds after the Big Bang, the universe expanded faster than light. Any information from before inflation would be stretched beyond our cosmic horizon, making it fundamentally unobservable regardless of technological advances. Quantum mechanics introduces additional temporal complexity. At the Planck time, approximately y-43 seconds after the Big Bang, our understanding of physics breaks down completely. General relativity and quantum mechanics provide contradictory descriptions of spacetime at such extreme scales. We cannot meaningfully discuss what happened before the Planck time without a theory of quantum gravity. These temporal boundaries create a hierarchy of observational limits. The cosmic microwave background represents our deepest direct view into cosmic history. Beyond that lies the dark age before recombination, accessible only through particle physics experiments that recreate primordial conditions. Even deeper lies the inflationary epoch, potentially forever beyond direct observation. And at the foundation lies the Planck era, where physics itself becomes uncertain. Dr. Alan Guth, who developed the theory of cosmic inflation, describes this as cosmic archaeology with missing artifacts. We can study the universe's recent history through direct observation, its intermediate history through physics experiments, and its earliest moments only through theoretical inference. The temporal boundary also affects how we interpret cosmic evolution. When we observe distant galaxies, we see them at different cosmic ages. The most distant galaxies appear as they were when the universe was less than 10% of its current age. These ancient galaxies show properties very different from modern ones. They were smaller, more chaotic, and actively forming stars at tremendous rates. But cosmic expansion means that these ancient galaxies have evolved dramatically since emitting the light we observe. The small, irregular galaxies we see in the early universe have likely merged and evolved into massive elliptical galaxies by now. We're observing cosmic evolution frozen in time, with each distance revealing a different chapter in galactic development. The Hubble Space Telescope's deep field observations revealed this cosmic timeline in stunning detail. The Hubble Ultra Deep Field, which exposed a tiny patch of sky for over 11 days, showed galaxies spanning more than 13 billion years of cosmic history. Each galaxy appears as it was when the universe had a different age, density, and expansion rate. Gravitational wave astronomy has recently opened another window into cosmic history. The LIGO and Virgo detectors observed the merger of black holes and neutron stars, events that occurred billions of years ago. These gravitational waves carry information about dense matter physics and strong gravitational fields that complement electromagnetic observations. Future gravitational wave detectors like LISA, the Laser Interferometer Space Antenna, will observe mergers from even earlier cosmic epochs. These observations might reveal information about the universe's matter content and expansion, history that is inaccessible through electromagnetic radiation. The temporal boundary creates profound implications for cosmic loneliness. As cosmic expansion accelerates, more galaxies will cross beyond our future observational reach. Future astronomers will see fewer galaxies than we do, and those they can observe will appear increasingly redshifted and faint. In approximately 100 billion years, cosmic expansion will have carried all other galaxies beyond the cosmic horizon. Future astronomers will inhabit a dark universe containing only their local galaxy group. They will have no way to discover that other galaxies ever existed, making cosmology impossible from their perspective. This cosmic isolation reveals deep connections between observation and existence. Our current ability to study cosmic history depends entirely on the universe's age and expansion rate. We exist during a special epoch when cosmic expansion hasn't yet hidden the universe's large-scale structure. Dr. Lawrence Krauss calls this the golden age of cosmology, a brief window in cosmic history when intelligent beings can study the universe's origins and evolution. Before this epoch, no stable structures existed to support complex chemistry. After this epoch, cosmic expansion will hide the evidence needed for cosmological discovery. The temporal boundary also raises questions about cosmic fine-tuning. The universe's properties seem precisely calibrated to allow complex structures to form and evolve. If cosmic expansion were slightly faster, galaxies would never have formed. If it was slightly slower, the universe would have collapsed before stars could synthesize heavy elements. These considerations suggest that our location in space and time may not be coincidental. We exist during the universe's brief period of maximum complexity, when cosmic expansion has created large-scale structure but hasn't yet begun to tear it apart. This temporal positioning might be necessary for the evolution of intelligence itself. As we approach the deepest questions about cosmic origins and ultimate fate, we begin to realize that time boundaries shape everything we can know about reality. The 93 billion light-year observable universe represents not just a spatial limit, but a temporal window, a brief glimpse into cosmic history surrounded by vast epochs we can never directly explore. The implications extend far beyond astronomy, touching the deepest questions about existence, knowledge, and our place in the cosmic order. Chapter 5. Infinite Mystery. Beyond the edge of everything we can see lies a realm so vast and unknowable that it dwarfs our observable universe the way the cosmos dwarfs a grain of sand. The 93 billion light-year sphere surrounding us contains perhaps 2 trillion galaxies. But this may represent less than 0.001% of what actually exists. Tonight, we're confronting the staggering reality that the universe extends far beyond our cosmic horizon, possibly infinitely, filled with wonders we can never hope to observe. The mathematics of cosmic inflation suggest that the universe underwent a period of exponential expansion during its first fraction of a second. During this inflationary epoch, space expanded by a factor of at least 1026, and possibly much more. If inflation lasted even slightly longer than the minimum required, the universe would be not just large, but unimaginably vast. Dr. Andre Lind, one of inflation's primary architects, calculates that cosmic inflation could have created a universe with a diameter exceeding 1,023 times the size of our observable region. To put this in perspective, if our observable universe were the size of a light bulb, the actual universe would be larger than Earth's orbit around the Sun. But even these mind-boggling numbers might underestimate reality. Eternal inflation theory suggests that the inflationary process never completely ends. While inflation stopped in our cosmic region 13.8 billion years ago, it continues in other areas, constantly creating new space faster than light can cross it. This process generates an infinite number of causally disconnected regions like our own observable universe. Each of these pocket universes evolves independently, potentially with different physical laws, particle masses, and fundamental constants. String theory predicts approximately 10,500 possible configurations of physical laws, a number so large that it exceeds the estimated number of atoms in our observable universe. Most of these configurations would create universes hostile to complex structures, but vast numbers would allow stars, planets, and possibly life to develop. The implications stagger the imagination. In an infinite universe with infinite variation, every possible arrangement of matter that doesn't violate physical laws must occur somewhere. This includes exact duplicates of Earth, perfect copies of yourself, and variations on cosmic history where different choices led to different outcomes. But infinity creates paradoxes that challenge our understanding of probability and uniqueness. In an infinite universe, every possible event occurs not just once, but infinitely many times. There are infinitely many Earths where dinosaurs never went extinct, infinitely many where humans evolved differently, and infinitely many where you made different decisions at every moment in your life. Max Tegmark of MIT has calculated the statistical distances to these duplicate regions. The nearest Earth identical to ours in every detail exists approximately 101,029 meters away, a distance so vast that it makes our observable universe seem like a point particle. Yet, in an infinite universe, such duplicates must exist. These considerations reveal deep questions about identity and meaning. If identical copies of you exist throughout the infinite cosmos, what makes your consciousness unique? Are you truly individual or one instance of a pattern repeated endlessly across space? These questions touch the foundations of philosophy and personal identity. The unobservable universe also raises profound issues about scientific knowledge. Modern cosmology makes strong claims about the universe's properties, its geometry, composition, and evolution. But these conclusions are based entirely on observations within our tiny cosmic bubble. We assume that physical laws remain constant throughout the infinite cosmos, but we have no way to verify this assumption. Different regions of an eternally inflating universe might have experienced different numbers of inflationary epochs, creating hierarchical structures of cosmic evolution. Some regions might be much older than ours, with civilizations billions of years more advanced. Other regions might be much younger, just beginning their star formation epochs. The possibility of advanced civilizations in unobservable regions creates what cosmologists call the Copernican conundrum. If intelligence is common throughout the infinite cosmos, Why do we appear to be among the first civilizations in our observable region? Are we truly early in the universe's history, or do observational selection effects hide evidence of earlier intelligence? Some theorists propose that advanced civilizations might engineer cosmic structures on such large scales that they affect the cosmic microwave background or other observable phenomena. The search for such cosmic archaeology represents a new frontier in the search for extraterrestrial intelligence. The unobservable universe also affects our understanding of cosmic fine-tuning. The precise values of physical constants that allow complex structures to form seem improbably perfect. In our observable region, the cosmological constant, the strong nuclear force, and the ratio of proton to electron mass are all calibrated to within narrow ranges that permit star formation, nuclear synthesis, and chemical complexity. But in an infinite multiverse, every possible combination of physical constants occurs somewhere. We naturally find ourselves in a region with laws hospitable to our existence, not because these laws are special, but because we couldn't exist in regions with different laws. This anthropic principle provides a statistical explanation for cosmic fine-tuning without requiring intelligent design. Yet the anthropic principle raises its own questions about probability and meaning. If we exist only because infinite variation ensures that some regions have suitable laws, what does this say about purpose and significance in the cosmos? Are we merely statistical accidents in an infinite lottery? Or does our existence reveal deeper principles about the nature of reality? Current and future observations will test some implications of cosmic infinity. The cosmic microwave background contains subtle patterns that reveal information about inflationary physics. The Planck satellite detected these patterns with unprecedented precision, finding evidence consistent with simple models of cosmic inflation. The James Webb Space Telescope is observing the universe's earliest galaxies, revealing how cosmic structure developed during the first billion years. These observations test whether our observable region is typical or special compared to the theoretical average of infinite cosmic variation. Gravitational wave astronomy offers another probe of cosmic infinity. Future detectors might observe gravitational waves from the inflationary epoch itself, carrying direct information about the physics that created cosmic exponential expansion. Such observations could reveal whether inflation was eternal or finite, and whether it created finite or infinite space. But perhaps the most profound implications involve consciousness and observation themselves. In an infinite universe, every possible observer exists infinitely many times. This includes observers with false memories, observers in simulated realities, and observers experiencing every conceivable variation of cosmic history. The Boltzmann brain paradox illustrates this problem. In an infinite universe, random thermal fluctuations will occasionally create conscious observers with false memories of a coherent history. Such randomly assembled brains would vastly outnumber observers, like ourselves, who evolved through conventional processes. This suggests that in an infinite cosmos, most observers would be hallucinating their apparent reality. These paradoxes reveal deep connections between cosmology, consciousness, and the nature of scientific knowledge. If most observers in an infinite universe experience false realities, what justifies our confidence in our own observations? How can we distinguish genuine cosmic history from elaborate hallucination? Dr. Sean Carroll and other cosmologists are exploring these questions through careful analysis of quantum mechanics, thermodynamics, and information theory. The answers may require new frameworks that connect the physics of infinity with the nature of conscious experience. As we contemplate the infinite mystery beyond our cosmic horizon, we begin to appreciate how much remains unknown about the universe's true nature. Our observable region, vast as it appears, may be just the tiniest sample of an incomprehensibly larger reality filled with wonders beyond imagination. The 93 billion light-year diameter of the observable universe represents not the edge of existence, but the limit of our knowledge, a boundary that reminds us of both the power and limitations of human understanding in the face of infinite cosmic mystery. Chapter 6. Accelerating isolation. The universe is not just expanding, it's accelerating its expansion. And this acceleration is gradually erasing the cosmos from our view. Tonight, we're discovering how dark energy, the most mysterious force in nature, is driving space apart faster than ever before, ensuring that the observable universe will eventually shrink rather than grow, leaving future astronomers in a dark and lonely cosmos with no evidence that other galaxies ever existed. In 1998, two independent teams of astronomers made a discovery that would fundamentally transform our understanding of cosmic fate. Saul Perlmutter, S Supernova Cosmology Project, and Brian Schmidt, S High Z Supernova Search Team, were using Type Ia supernova as standard candles to measure the expansion history of the universe. These stellar explosions always reach approximately the same peak brightness, making them ideal cosmic distance indicators. Both teams expected to find evidence that cosmic expansion was slowing down due to gravitational attraction between galaxies. Instead, they discovered something completely unexpected. Distant supernova appeared fainter than predicted, indicating that cosmic expansion was actually accelerating. The universe wasn't just growing larger, it was growing larger at an ever-increasing rate. This discovery revealed the existence of dark energy, a repulsive force that comprises approximately 68% of the universe's total energy density. Unlike gravity, which attracts matter together, dark energy pushes space itself apart. As the universe expands and matter density decreases, dark energy's influence becomes increasingly dominant. The Planck satellite measurements confirmed that dark energy has remained remarkably constant throughout cosmic history. Its energy density doesn't dilute as space expands, meaning that larger volumes of space contain proportionally more dark energy. This creates a runaway effect. As the universe grows, dark energy becomes more powerful relative to gravity, driving ever faster expansion. Einstein's cosmological constant provides the simplest model for dark energy. He originally introduced this constant to balance gravity and create a static universe, but observations show it perfectly describes the acceleration we observe. The cosmological constant represents the energy density of empty space itself, the quantum. Vacuum has a small but non-zero energy that manifests as cosmic repulsion. But the cosmological constant creates profound puzzles. Quantum field theory predicts that vacuum energy should be enormous, roughly 120 orders of magnitude larger than what we observe. This represents perhaps the worst theoretical prediction in the history of physics. The mechanism that reduces vacuum energy to its observed tiny but non-zero value remains completely mysterious. Alternative dark energy models propose dynamic fields that evolve over time. Quintessence theories suggest that dark energy strength could change throughout cosmic history. Phantom energy models predict that dark energy might grow stronger with time, leading to a big rip where accelerating expansion eventually tears apart stars, planets, and even atoms themselves. Current observations cannot distinguish between these possibilities. Dark energy appears constant within measurement uncertainties, but small changes in its strength could dramatically alter cosmic evolution over billions of years. Future missions like the Nancy Grace Raman Space Telescope and the European Space Agency's Euclid satellite will measure dark energy properties with unprecedented precision. The acceleration has already begun to affect what we can observe. Galaxies currently near the edge of our observable horizon are moving away from us at velocities approaching the speed of light. Light emitted from these galaxies today will never reach Earth because cosmic expansion stretches space faster than the light can cross it. This creates a counterintuitive situation. We can see galaxies that are now causally disconnected from us. We observe their ancient light, but no information or influence can travel between us and these distant systems. They exist in our past, but not in our future. The observable universe contains objects we can never hope to visit, communicate with, or influence in any way. The cosmic event horizon marks the boundary beyond which events occurring today will never be observable from Earth. This horizon is currently located at approximately 16 billion light-years away, much closer than the particle horizon that defines the edge of our observable universe. Galaxies beyond the event horizon are effectively isolated from us forever. As cosmic acceleration continues, this event horizon will remain fixed while our particle horizon continues to expand slowly. Over time, more galaxies will cross the event horizon and disappear from our future observations. The James Webb Space Telescope might be seeing some distant galaxies for the last time, as their light will become too redshifted to detect within the next few billion years. Dr. Lawrence Krauss has calculated the timeline of cosmic isolation. In approximately 100 billion years, all galaxies outside our local group will have moved beyond our observable horizon. The Milky Way, Andromeda, and their satellite galaxies will merge into a single elliptical galaxy surrounded by empty space. Future astronomers in this far future will observe a universe that appears completely different from ours. They will see a single galaxy and an otherwise empty cosmos, with no evidence that other galaxies ever existed. The cosmic microwave background will have redshifted beyond detectability. The universe will appear static and eternal from their perspective. These future scientists will be unable to discover the Big Bang, cosmic evolution, or the existence of other galaxies. Cosmology, the science that has revealed so much about our origins and fate, will become impossible. The universe will hide its own history through the simple passage of time and continued expansion. This cosmic censorship has already begun. We observe fewer galaxies today than we would have 5 billion years ago, and we will observe fewer galaxies 5 billion years from now. Each passing moment carries more information beyond our cosmic horizon, making the universe appear progressively more isolated and mysterious. The acceleration also affects our understanding of cosmic infinity. While the universe may be infinite in size, the accelerating expansion ensures that we can interact with only a finite region. Even if infinite civilizations exist throughout infinite space, cosmic acceleration will gradually isolate each civilization within its own expanding bubble. String theory and quantum gravity suggest that accelerating expansion might trigger transitions to new vacuum states with different physical laws. If dark energy represents a metastable state rather than the true vacuum, quantum tunneling could nucleate bubbles of space with altered physics. These bubbles would expand at light speed, potentially sterilizing any life they encounter. The anthropic implications are profound. We exist during a special epoch when cosmic acceleration has created large-scale structure, without yet destroying our ability to observe cosmic history. Earlier in cosmic history, the universe was too dense and violent for complex structures to form. Later in cosmic history, cosmic acceleration will hide evidence of cosmic evolution. This temporal fine-tuning suggests that the emergence of intelligence might be correlated with cosmic expansion history. Civilizations can only discover their cosmic origins during narrow windows when expansion has created observability without yet destroying evidence of cosmic evolution. Dark energy also raises questions about the ultimate fate of physical law itself. If dark energy continues to accelerate expansion, space will eventually expand so rapidly that quantum fluctuations become stretched across cosmic scales. Virtual particles will be separated before they can annihilate, potentially creating real particles from vacuum energy. This process, known as de Sitter space particle creation, suggests that accelerating expansion might be thermodynamically unstable. The cosmic horizon in an accelerating universe has an associated temperature and entropy, similar to black hole horizons. This temperature might eventually drive transitions to new vacuum states or cause the spontaneous creation of matter and energy. The discovery of cosmic acceleration represents one of the most important and mysterious findings in modern cosmology. It reveals that we live in a universe dominated by a force we don't understand, heading toward a fate we can barely imagine. The 93 billion light-year observable universe represents a temporary island of observability in an accelerating cosmos that will eventually hide most of reality from view. As we contemplate this accelerating isolation, we begin to appreciate how precious our current cosmic perspective truly is. We exist during perhaps the only epoch in cosmic history when intelligent beings can discover the universe's origins, evolution, and large-scale structure. A brief window of enlightenment between cosmic obscurity and cosmic loneliness. Chapter 7. Quantum Horizons at the Deepest Level. The boundaries of the observable universe emerge from quantum mechanics itself. The horizon that limits what we can see isn't just about expansion or light travel time. It is woven into the fundamental structure of quantum spacetime, creating connections between black holes, thermodynamics, and cosmic observation that reveal reality to be stranger than we ever imagined. Tonight, we're re-exploring how quantum physics transforms our understanding of cosmic boundaries and suggests that the universe's edge might have temperature, entropy, and information content. The connection between quantum mechanics and cosmic horizons began with Stephen Hawking's groundbreaking work on black holes in the 1970s. Hawking discovered that black holes aren't completely black. They emit thermal radiation due to quantum effects near their event horizons. This Hawking radiation emerges from the quantum vacuum itself, where virtual particle pairs constantly appear and annihilate. Near a black hole's event horizon, quantum fluctuations occasionally separate particle pairs before they can recombine. One particle falls into the black hole while its partner escapes to infinity. The escaping particle becomes real Hawking radiation, while the infalling particle carries negative energy into the black hole, gradually reducing its mass. Black holes slowly evaporate through this quantum process. But Hawking's analysis revealed something even more profound. The event horizon behaves like a thermodynamic system with well-defined temperature and entropy. The horizon's temperature is inversely proportional to the black hole's mass, while its entropy is proportional to the horizon's surface area. These relationships suggest deep connections between gravity, quantum mechanics, and information theory. Jacob Bekenstein had earlier proposed that black holes have entropy proportional to their surface area rather than their volume. This Bekenstein-Hawking entropy formula implies that information is somehow encoded on the horizon's two-dimensional surface, even though the black hole appears three-dimensional. This holographic principle has become central to modern theories of quantum gravity. The cosmic horizon shares these mysterious quantum properties. Our observable universe is bounded by a horizon, the surface of last scattering where the cosmic microwave background originates. Like black hole horizons, this cosmic horizon has an associated temperature and entropy that emerge from quantum effects in curved spacetime. The Unruh effect provides another crucial connection between acceleration and quantum temperature. William Unruh discovered that an accelerating observer experiences thermal radiation from the quantum vacuum, even in completely empty space. The vacuum that appears cold and empty to an inertial observer appears warm and filled with thermal radiation to an accelerated observer. Cosmic expansion creates similar acceleration effects. As space expands, observers experience cosmic acceleration relative to distant reference frames. This acceleration generates thermal radiation from the quantum vacuum, giving the cosmic horizon a temperature similar to Hawking radiation from black holes. The Gibbons-Hawking temperature describes this cosmic thermal radiation. For our current universe with accelerating expansion driven by dark energy, this temperature is approximately 10 to 30 Kelvin. incredibly cold, but non-zero. Future observations might eventually detect this cosmic thermal radiation as a faint background glow beyond the cosmic microwave background. Quantum field theory in curved spacetime reveals additional complications. Virtual particles that exist briefly in flat spacetime can become real particles in expanding spacetime. The expansion stretches virtual particle wavelengths, preventing particle-antiparticle pairs from recombining. This creates real particles from vacuum energy through a process called cosmological particle creation. During cosmic inflation, this particle creation mechanism generated the density fluctuations that would eventually become stars and galaxies. Quantum fluctuations in the inflated field were stretched to cosmic scales by exponential expansion, creating the seeds of all cosmic structure. We exist because quantum mechanics amplified microscopic fluctuations into macroscopic density variations. The cosmic microwave background radiation preserves these quantum origins. The tiny temperature variations mapped by the Planck satellite represent quantum fluctuations from the inflationary epoch, stretched and frozen by cosmic expansion. When we observe cosmic microwave background patterns, we're seeing the quantum mechanical origins of cosmic structure itself. But quantum mechanics creates paradoxes for cosmic observation. The quantum vacuum contains virtual particles with all possible momenta and energies. In curved spacetime, the definition of vacuum becomes observer-dependent. What appears empty to one observer may appear filled with particles to an accelerated observer. This observer dependence challenges our understanding of objective reality. If the contents of space depend on the observer's motion and gravitational environment, what constitutes the true state of the quantum vacuum? Different observers disagree about the number and energy of particles in seemingly empty space. Quantum entanglement adds further complexity to cosmic horizons. When particle pairs are created near horizons, the escaping and infalling particles remain quantum entangled. This creates correlations between regions inside and outside the horizon, even though no information can travel between them. For black holes, this entanglement creates the information paradox. Information falling into a black hole becomes quantum entangled with Hawking radiation escaping from the hole. As the black hole evaporates, quantum entanglement should preserve all information, but general relativity suggests that information is destroyed when it crosses the event horizon. Similar paradoxes arise for cosmic horizons. Information about distant regions of the universe becomes inaccessible as cosmic expansion carries them beyond our horizon. Quantum mechanics suggests this information should be preserved in some form, perhaps encoded in subtle correlations in the cosmic microwave background or other observable phenomena. String theory and loop quantum gravity propose that spacetime itself has quantum structure at the Planck scale, approximately 10 to 35 meters. At this scale, the smooth fabric of spacetime described by general relativity breaks down into quantum foam, a frothy mixture of virtual black holes, wormholes, and exotic topological structures. These quantum spacetime effects might affect cosmic horizons in fundamental ways. The boundary between observable and unobservable regions might not be sharp, but fuzzy, with quantum tunneling allowing limited information exchange across the horizon. Quantum gravity might reveal that horizons are emergent properties that arise from more fundamental quantum information structures. The holographic principle suggests that all information within our observable universe is encoded on its two-dimensional boundary. If true, this means that our three-dimensional experience of space emerges from information processing on the cosmic horizon's surface. We might be holographic projections of data stored on the edge of space itself. Recent developments in quantum information theory support this holographic perspective. The ADCC correspondence, discovered by Juan Maldacena, demonstrates mathematical equivalence between gravity in three-dimensional space and quantum field theory on a two-dimensional boundary. This holographic duality suggests that gravity itself might be an emergent property of quantum information processing. These insights transform our understanding of cosmic boundaries. Rather than simple limits on observation, horizons might represent fundamental information processing surfaces where quantum effects generate the appearance of three-dimensional space. The 93 billion light-year diameter of our observable universe might emerge from quantum computation on its boundary. Experimental tests of these quantum horizon effects remain challenging, but not impossible. Future gravitational wave detectors might observe quantum signatures in the cosmic gravitational wave background. Advanced cosmic microwave background experiments might detect quantum correlations that reveal information about physics beyond our horizon. Quantum computers offer another experimental avenue. Simulating quantum field theory in curved spacetime requires enormous computational resources. But quantum computers might eventually model horizon physics directly. Such simulations could test whether quantum effects near horizons generate the thermodynamic properties that Hawking and others predicted. The intersection of quantum mechanics and cosmic horizons also raises profound questions about consciousness and observation. If horizons have quantum properties similar to thermodynamic systems, they might process information in ways that resemble computation or even primitive forms of cognition. Some physicists speculate that the universe itself might be a vast quantum computer, processing information through the evolution of quantum fields in curved spacetime. From this perspective, cosmic horizons represent interfaces between different computational domains, processing boundaries where quantum information is transformed and transmitted. As we approach the deepest questions about cosmic boundaries and quantum reality, we begin to see how the 93 billion light-year observable universe might be just one facet of a more fundamental quantum information structure. The horizon that limits what we can see might also be the computational surface that generates everything we experience as physical reality. These quantum insights suggest that the observable universe as boundary represents more than just a limit on observation. It might be the edge of reality itself, where quantum computation generates the appearance of space-time and matter from pure information. Chapter 8. Measurement Paradox. The act of measuring cosmic distances creates paradoxes that challenge our fundamental understanding of what it means to know the size of the universe. Every technique we use to determine that the observable universe is 93 billion light-years across depends on assumptions about physics that become uncertain at the very scales we're trying to measure. Tonight, we're exploring how cosmic measurement pushes the boundaries of scientific knowledge and reveals deep connections between observation, reality, and the limits of human understanding. When Edwin Hubble first measured the expansion of the universe in 1929, he faced an unprecedented challenge. How do you calibrate distance measurements across cosmic scales where no direct verification is possible? His solution relied on the cosmic distance ladder, a hierarchy of measurement techniques that extends from nearby objects with known distances to the most remote galaxies visible. The foundation of this ladder rests on geometric parallax, the apparent shift in nearby stars' positions as Earth orbits the Sun. The European Space Agency's Gaia satellite has now measured parallax distances to over 1.3 billion stars with unprecedented precision, creating the most accurate map of our local galactic neighborhood ever assembled. But parallax measurements become impossible beyond a few thousand light years. For greater distances, astronomers rely on standard candles, objects whose intrinsic brightness is known or can be calculated. Cepheid variable stars, discovered by Henrietta Swan Leavitt, pulsate with periods directly related to their luminosity. By measuring a Cepheid's pulsation period, astronomers can calculate its true brightness and compare this with its observed brightness to determine distance. The problem is that each step in the cosmic distance ladder depends on the accuracy of all previous steps. Errors compound as we reach toward greater distances, and systematic uncertainties become increasingly difficult to identify and correct. When we claim that the observable universe is 93 billion light-years across, we're extrapolating from measurements that are themselves based on chains of assumptions extending across 13.8 billion years of cosmic evolution. Type E supernova serve as the most distant standard candles, allowing distance measurements to galaxies billions of light-years away. These stellar explosions occur when white dwarf stars accrete matter from companion stars until they reach a critical mass threshold and explode with remarkably consistent peak brightness. But recent observations have revealed subtle variations in supernova properties that challenge their use as perfect standard candles. The Pantheon plus Supernova Catalog, compiled from observations of over 1,700 Type Ia supernova, shows systematic trends in supernova brightness that correlate with their host galaxy properties, cosmic environment, and explosion characteristics. These correlations suggest that supernova aren't perfectly standardizable, introducing uncertainties that propagate through all cosmic distance measurements. Even more troubling, different measurement techniques often disagree about fundamental cosmic parameters. The Hubble constant, the rate of cosmic expansion, shows different values depending on how it's measured. Local measurements using Cepheid variables in supernova yield a value around 73 kilometers per second (MPC), while measurements from the cosmic microwave background indicate approximately 67 kilometers per second (MPC). This Hubble tension represents a genuine crisis in cosmology. The discrepancy exceeds measurement uncertainties and has persisted despite increasingly precise observations. Either systematic errors plague our measurement techniques, or our fundamental understanding of cosmic evolution is incomplete. Both possibilities challenge the reliability of cosmic distance determinations. The cosmic microwave background provides an independent approach to cosmic measurement, but it relies on detailed theoretical models of cosmic evolution. The Planck satellite measured tiny temperature variations in this ancient radiation with extraordinary precision, revealing acoustic oscillations that occurred when the universe was only 380,000 years old. These baryon acoustic oscillations create a standard ruler, a characteristic scale determined by the speed of sound waves in the early universe. By comparing the apparent size of these oscillations on the sky with their calculated physical size, astronomers can determine distances to the cosmic microwave background source. This measurement provides the foundation for calculating the observable universe's current size. But this technique assumes that our understanding of early universe physics is correct. The calculation depends on precise knowledge of the universe's matter and energy content, the physics of recombination, and the behavior of cosmic expansion throughout 13.8 billion years of history. Each assumption introduces potential systematic errors that could affect our cosmic size estimates. Gravitational lensing offers another cosmic measurement tool that seems independent of traditional distance indicators. When massive galaxy clusters bend light from background galaxies, the amount of lensing reveals information about distances, masses, and cosmic geometry. The time delays between multiple images of gravitationally lensed quasars provide particularly powerful constraints on cosmic expansion. However, gravitational lensing measurements depend on our understanding of mass distribution within galaxy clusters, including the properties of dark matter halos and the effects of structure formation. Recent observations of galaxy cluster collisions, such as the famous bullet cluster, reveal complex interactions between dark matter and ordinary matter that complicate lensing analyses. The fundamental problem is that cosmic measurements push far beyond the realm where direct verification is possible. We can never travel to distant galaxies to verify our distance measurements, and we cannot repeat cosmic evolution to test our theoretical models. Cosmology must be constructed from indirect inferences based on limited observational data and theoretical frameworks that themselves require validation. Quantum mechanics adds another layer of measurement uncertainty. The Heisenberg uncertainty principle limits the precision with which we can simultaneously measure certain properties of quantum systems. While these limits don't directly affect large-scale cosmic measurements, they do influence our understanding of the early universe conditions that determined cosmic evolution. During cosmic inflation, quantum fluctuations in the inflation field created the density perturbations that eventually became stars and galaxies. The statistical properties of these quantum fluctuations are imprinted in the cosmic microwave background and large-scale structure patterns we observe today. But quantum mechanics prohibits perfect knowledge of the initial conditions that determined cosmic evolution. This quantum indeterminacy means that cosmic evolution is inherently statistical. Even with perfect knowledge of physical laws, we cannot predict the exact outcome of cosmic structure formation. Multiple universe realizations with slightly different quantum initial conditions would produce observably different cosmic architectures. The measurement of cosmic acceleration through distant supernova illustrates these fundamental limitations. The discovery of dark energy relies on comparing the observed brightness of distant supernova with theoretical predictions based on standard cosmological models. But these predictions assume that physical laws have remained constant throughout cosmic history, and that our understanding of stellar evolution is complete. Future astronomical observations will test these assumptions with unprecedented precision. The Nancy Grace Raman Space Telescope will measure distances to thousands of supernova across cosmic history, potentially revealing whether dark energy properties have changed over time. The extremely large telescope will directly measure cosmic expansion by observing how the redshifts of distant quasars change over decade-long timescales. But each new measurement technique introduces its own systematic uncertainties and theoretical dependencies. Direct measurement of cosmic expansion through redshift drift will require extraordinary instrumental stability and precise understanding of stellar evolution, atmospheric effects, and gravitational influences on telescope precision. The philosophical implications extend far beyond astronomy. If our most fundamental cosmic measurements depend on chains of assumptions that cannot be independently verified, what does this say about the nature of scientific knowledge itself? How can we distinguish between genuine cosmic properties and artifacts of our measurement techniques? Karl Popper emphasized that scientific theories must be falsifiable to be meaningful, but many cosmic measurements approach the limits of falsifiability. We cannot perform controlled experiments on cosmic evolution, and alternative theoretical frameworks often make predictions that differ only at levels of precision that challenge our observational capabilities. Thomas Kuhn's analysis of scientific revolutions suggests that major advances often require abandoning established measurement frameworks in favor of entirely new approaches. The history of cosmology supports this perspective. Each major breakthrough, from the discovery of cosmic expansion to the detection of cosmic acceleration, required measurements that challenged existing theoretical frameworks. The measurement paradox reveals deep connections between cosmic scale and epistemological limits. The 93 billion light-year diameter of the observable universe represents the culmination of humanity's most ambitious measurement project. But it also exposes the fundamental challenges of gaining knowledge about systems that transcend direct human experience. As we approach the limits of cosmic measurement, we must confront questions about the relationship between observation and reality that extend far beyond astronomy into the deepest problems of philosophy and human knowledge.